What if the space between stars isn't empty at all? What if the vast, silent stretches of darkness that we've always dismissed as mere nothing, the cosmic gaps we assume are just the absence of something, are in fact the most dangerous, the most mysterious, and perhaps the most alive regions in the entire universe? Tonight, we venture into the interstellar medium, that colossal, invisible ocean that surrounds every star, including our own sun. And I want you to sit with something uncomfortable for the next hour, because this journey will take us from the reassuring arms of settled science through the unsettling corridors of what we don't yet understand, and right up to the edge of something that no textbook has fully explained. We call it empty space. We joke about it. We use it as a metaphor for meaninglessness. There's nothing there, we say, it's just space. But what if that's wrong? What if empty is the most misleading word in all of astronomy? What if the interstellar medium, that thin, cold, impossibly vast sea of gas and dust and magnetic fields and cosmic rays churning between every star, is not empty but seething, not silent but humming with forces we are only beginning to measure? And here's the question that should keep you awake tonight. Our solar system is moving through this medium. Right now, as you watch this video, we are not stationary. Our sun, our entire planetary system, every living thing that has ever existed on this Earth, we're all plowing through the interstellar medium at roughly 70,000 miles per hour. We are inside a protective bubble called the heliosphere, and that bubble is what stands between us and everything the interstellar medium contains. And here's the thing, that bubble may be changing. Recent data from NASA's Voyager probes, the only human-made objects to have actually crossed into interstellar space, suggests that the boundary between our heliosphere and the interstellar medium is far more complex, far more dynamic and far more turbulent than our models predicted. So tonight, we're going to ask the question that serious scientists are beginning to ask in their papers and their observatories and their late-night research conversations. What is really out there in the space between the stars? What does it mean that we are moving through it? What happens if that protective bubble weakens or shifts or encounters something unexpected? And most provocatively of all, what if the interstellar medium is not just a hazard, but a messenger? What if it carries information and perhaps more from the very first moments of the universe's existence? Let's begin. But first, a warning. This video will walk a careful line between what the science actually says and what speculation, extrapolation, and imagination suggests might be true. I will tell you clearly when we cross from one territory into the other. The universe is strange enough without exaggeration, but it is also strange enough to make exaggeration feel almost unnecessary. The space between stars is not nothing. It never was. Before we go deeper into this story, and believe me, it goes very deep, if you're fascinated by the hidden architecture of the cosmos and the science that's beginning to pull back the curtain on it, make sure you hit that subscribe button right now and ring the notification bell so you never miss a new deep dive. Drop a comment below and tell me what time it is where you're watching from and what country you're in. I genuinely love looking through these comments and seeing how far across this pale blue dot these videos travel. Someone watching this right now is sitting in Johannesburg or Manila, or a small town in rural Canada, and you're all looking up at the same interstellar medium that we're about to explore together. That's extraordinary to me. And if the research that goes into these videos, the hours of reading papers, tracking down scientists and trying to translate the genuinely mind-bending into something that makes sense at 2 a.m. If that matters to you, a like really does help this channel reach more curious minds. Every click is one more person looking up instead of down. Now, let's talk about the space between the stars. Let's start with the facts, just the facts, because they are remarkable enough on their own before we add a single layer of speculation. The interstellar medium, or ISM, is the matter and radiation that exists in the space between star systems within a galaxy. It is not nothing. It is composed of gas, primarily hydrogen and helium in various states, dust, cosmic rays, magnetic fields, and electromagnetic radiation. It is, by Earth standards, extraordinarily thin. A cubic centimeter of the ISM contains, on average, about 1 atom. By comparison, a cubic centimeter of the air you're breathing right now contains approximately 27 billion atoms. So in one sense, the ISM is almost incomprehensibly empty. You could pass through it for thousands of years and never notice in any physical sense that anything was there at all. That's the reassuring headline. That's what the textbooks lead with, and they're not wrong, but here's what they often don't tell you. The ISM is not uniform. It is not a smooth, evenly distributed fog of thin gas. It is wildly, chaotically structured. There are cold, dense molecular clouds where the temperature drops to just 10 Kelvin, colder than anywhere on Earth has ever been. And there are vast, scorching regions called hot ionized bubbles where temperatures spike to 1,000,000 Kelvin or more. There are magnetic filaments, shock waves propagating from ancient supernovae, vast sheets of dust that can stretch hundreds of light years, and rivers of charged particles flowing along invisible magnetic field lines. The ISM is, in short, an ecosystem, a dynamic, violent, constantly shifting ecosystem that spans the entire galaxy. Now, where are we in relation to all of this? We are inside it. We have always been inside it. But, and this is crucial, we are protected from it. Our sun, like all stars, generates a powerful outflow of charged particles called the solar wind. This solar wind creates a vast bubble around the solar system, the heliosphere, that extends far beyond the orbit of Pluto. It acts as a shield, deflecting and slowing the interstellar medium before it can reach us. NASA's Voyager 1 spacecraft crossed the heliopause, the boundary where the solar wind loses its dominance and the interstellar medium begins, in 2012, becoming the first human-made object to enter interstellar space. What it found there was not empty. It was full. It was denser, hotter, and more magnetically complex than models had predicted. The official position of mainstream science is clear. The interstellar medium poses no significant direct threat to life on Earth. The heliosphere is robust. Our sun's output is stable. We have billions of years ahead of us before the sun begins to change in ways that would compromise that protection. This is almost certainly correct, and I want you to hold on to that reassurance because we're going to need it later. But the deeper you look at the interstellar medium, the more a quiet, nagging question begins to form in the back of your mind. The heliosphere is not static. It breathes. It responds to the sun's activity cycle, expanding and contracting over decades, and it also responds to what it's moving through. As our solar system travels around the center of the Milky Way on its roughly 225 million-year orbit, it passes through different regions of the ISM, some thin and quiet, some dense and turbulent. We cannot know with certainty what our heliosphere looked like when it was passing through a dense molecular cloud hundreds of millions of years ago. We cannot know how much the cosmic ray flux reaching Earth changed. We cannot know exactly what the ISM looked like the last time a nearby star went supernova and sent a wave of high-energy particles washing across our neighborhood. We can only know what it looks like right now. And right now we are passing through something called the local interstellar cloud, a warm, partially ionized region of gas about 30 light-years across. It is not particularly dense, it is not particularly threatening, but the local interstellar cloud has an edge, and beyond that edge the ISM changes. The question nobody can fully answer yet: what happens when we reach that edge? Let's talk about scale for a moment, because the numbers involved in the interstellar medium are so extreme that our brains genuinely struggle to process them. And that struggle matters for everything that comes after. The distance from our sun to the nearest star system, Alpha Centauri, is approximately 4.24 light-years. That's the distance light, the fastest thing in the universe, travels in 4.24 years. In miles, that's roughly 25 trillion miles. If you drove a car at highway speed without stopping, it would take you approximately 50 million years to get there. And Alpha Centauri is our nearest neighbor. Now consider, the Milky Way galaxy is about 100,000 light-years across. Within it, there are somewhere between 100 billion and 400 billion stars. The average distance between stars in our region of the galaxy is about 5 to 6 light-years. That means the interstellar medium fills an almost unimaginably vast volume. The combined interior of a galaxy containing hundreds of billions of stellar systems, all of it connected by this thin, dynamic, churning medium. And yet, despite being almost empty by earthly standards, the ISM contains a staggering total mass. The total mass of gas in the Milky Way's ISM is estimated at around 10 billion solar masses, 10 billion times the mass of the Sun. Distributed across 100,000 light-years of space, it's thin, but it is definitively not nothing. Now let's talk about some of the specific components, because the variety is extraordinary. The ISM exists in several distinct phases. The cold neutral medium, temperatures around 50 to 100 Kelvin, densities of around 20 to 50 atoms per cubic centimeter. The warm neutral medium, temperatures around 6,000 Kelvin, densities around 0.5 atoms per cubic centimeter. The warm ionized medium, temperatures around 8,000 Kelvin, and the hot ionized medium, temperatures of 1,000,000 Kelvin or more, created by supernova shockwaves with densities so low that even thin feels like an exaggeration. To put the temperature range in perspective, the difference between the coldest molecular clouds and the hottest ionized bubbles in the ISM is greater than the temperature difference between deep space and the surface of the Sun. These regions coexist in the same galaxy, sometimes separated by distances that seem enormous on human scales, but are minuscule on galactic ones. And then there's the dust. About 1% of the ISM by mass is interstellar dust. Tiny solid particles, mostly silicates and carbonaceous materials, ranging in size from a few molecules to about 1/10 of a millimeter. These dust grains are responsible for the dark lanes you see in photographs of galaxies and nebulae. They absorb and scatter starlight, making distant stars appear dimmer and redder than they actually are, an effect called interstellar reddening. But interstellar dust is more than a visual curiosity. It is a chemical laboratory. Atoms and molecules stick to dust grain surfaces, and in the cold dark of a molecular cloud, chemical reactions occur that would be impossible in isolation. Water ice, methanol, ammonia, complex organic molecules. These form on the surfaces of interstellar dust grains and are eventually incorporated into the clouds of material that collapse to form new stars and planetary systems. In other words, the chemistry of life may have begun not on Earth, but in the space between stars. The interstellar medium may be not just the context in which our solar system exists, but the origin of some of the molecules that made life possible. That's not speculation. That's peer-reviewed science. But what if the ISM's role in shaping life doesn't stop there? What if the chemical influence of the interstellar medium on life is not just a historical event, something that happened 4.5 billion years ago when our solar system formed, but an ongoing process? What if the ISM is still shaping us right now, through what it's delivering to us in the form of cosmic rays, interstellar dust that drifts into our inner solar system, and complex molecules that rain down on Earth in meteorites? That is not yet speculation. That is in fact a rich area of scientific research. The fields of astrochemistry and astrobiology take these questions very seriously. But here's the question that opens the door to something more unsettling. If the ISM delivered the building blocks of life to our planet, what else might it deliver? And what if, as our solar system moves into different regions of the ISM, the nature of what it delivers changes? Here is where things get genuinely strange, and I mean that in the most literal scientific sense of the word. In 2009, data from the IBEX spacecraft, the Interstellar Boundary Explorer, revealed something that stopped researchers cold. IBEX was designed to map the boundary between our heliosphere and the interstellar medium by detecting neutral atoms that flow in from outside. These atoms, traveling at roughly 50,000 miles per hour, pass right through the heliosphere and carry information about the ISM they came from. What IBEX found was a ribbon, an enormous curved ribbon of unexpectedly intense emission of energetic neutral atoms, stretching across roughly 1/3 of the sky. No one had predicted it. No existing model of the ISM had anticipated it. And to this day, despite more than a decade of analysis and debate, there is no consensus explanation for exactly what causes it. Let's be precise here. Scientists have theories, and some are more favored than others. The leading hypothesis involves the way that hydrogen atoms from the solar wind interact with the interstellar magnetic field. But the ribbon's exact geometry, its variation over time, and the specific physical mechanism that generates it remain active areas of research and genuine scientific disagreement. This is unusual. In most areas of planetary science, we understand what we're looking at even if we can't explain every detail. The ibex ribbon is one of those rare discoveries that genuinely surprised the entire field. But wait, it gets stranger. NASA's Voyager probes, when they crossed the heliopause and entered interstellar space, Voyager 1 in 2012, Voyager 2 in 2018, both detected something unexpected on the other side of the boundary. The magnetic field in the outer heliosheath, the region just inside the heliopause, and the magnetic field in the very local interstellar medium outside it appeared to be more aligned than models had predicted. This sounds technical, but its implication is significant. It suggests that the heliosphere and the interstellar medium around it are interacting in ways we don't fully understand, with the interstellar magnetic field perhaps shaping and compressing the heliosphere from outside. Our protective bubble is not floating freely in a neutral, indifferent medium. It is being shaped by what surrounds it. And then there's the data from Voyager 1 in 2012, just as it crossed the heliopause. Researchers expected to see a sharp drop in the intensity of particles accelerated by the sun's solar wind, and a sharp increase in galactic cosmic rays from outside. What they actually found was more complex. The solar wind particles dropped off as expected, but the galactic cosmic rays increased in a more gradual, layered pattern, suggesting the boundary region is not a clean line, but a complex, multi-layered transition zone. Now let's add another layer of strangeness. Recent research using observations from the IBEX spacecraft and the Cassini mission has led some scientists to propose a radical rethinking of the shape of the heliosphere itself. The traditional model has always depicted the heliosphere as comet-shaped, a rounded nose plowing through the ISM with a long tail stretching out behind it. But new data suggests it might actually be shaped more like a crescent or a croissant, a toroidal or spheroidal structure with a much shorter tail than previously believed. If that's true, it changes our understanding of how effectively the heliosphere deflects cosmic rays and interstellar material. It changes our models of what the interstellar medium can and cannot reach as it flows past our solar system. And this raises the question I want to leave with you at the end of this chapter. If we have been wrong about the shape of our own protective bubble, and we have been surprised by what Voyager found at the boundary, and we cannot fully explain the ibex ribbon, then how confident can we really be in our understanding of what the interstellar medium actually contains and what it's doing to us right now? The science does not suggest we are in immediate danger. I want to be clear about that. But the science does suggest that we are still in the early chapters of understanding what surrounds us. And early chapters are always the most surprising. Let me be direct with you. This is the chapter where we ask the worst-case question head-on and where I give you the most honest answer science can provide. Could the interstellar medium kill us? The short answer is not directly and not without conditions that would require an extraordinary sequence of events over extraordinarily long timescales. Let me explain why, and let me explain what those extraordinary conditions actually look like. First, the direct threat. Could interstellar gas and dust penetrate the heliosphere and directly affect Earth? Under normal circumstances, no. The solar wind creates a pressure that keeps interstellar material pushed back beyond the heliopause, roughly 100 to 120 astronomical units from the Sun. Even if some fraction of interstellar material does slip through, and tiny amounts of interstellar dust have in fact been detected by Cassini inside the solar system, the quantities are minuscule. They would need to increase by many orders of magnitude to pose any kind of environmental threat. Second, cosmic rays. The interstellar medium is filled with cosmic rays, high-energy particles, mostly protons, accelerated to near light speed by supernova shock waves and other high-energy processes. The heliosphere partially shields Earth from galactic cosmic rays by deflecting them with the solar wind's magnetic field. During periods of lower solar activity, this shielding is somewhat reduced, and cosmic ray flux at Earth's surface increases modestly. But even at maximum cosmic ray flux during solar minimums, the increase is not remotely close to dangerous levels for humans or most life. However, and this is a significant however, there is a real and scientifically serious scenario in which the ISM could, over geological timescales, affect Earth's climate. This scenario does not require science fiction. It requires only that our solar system move as it does through different regions of the ISM. Roughly every 135 million years or so, our solar system completes one orbit around the Milky Way. During that orbit, we pass through the Milky Way's spiral arms, which are regions of denser star formation and therefore denser interstellar gas and dust. When our heliosphere encounters a significantly denser patch of the ISM, two things can happen. One, the heliosphere is compressed. The increased external pressure pushes the heliopause closer to the Sun, reducing the volume of the protective bubble. In extreme cases, some researchers have speculated that this compression could push the heliopause inside the orbit of Earth, exposing our planet directly to the interstellar medium. 2. The increased density of interstellar dust flowing into the inner solar system could affect the amount of sunlight reaching Earth. Not dramatically, but enough over long periods to contribute to cooling trends. Have these effects actually happened? Some researchers believe they have. There are intriguing correlations, though not yet definitively proven causations, between the times when the solar system was passing through denser regions of the ISM and periods of glaciation in Earth's geological record. This bears repeating. These are correlations that researchers are studying. They are not confirmed causal links. The climate of Earth is influenced by dozens of factors: orbital variations, volcanic activity, greenhouse gas concentrations, solar luminosity, and attributing ice ages to ISM density is a hypothesis, not a conclusion. But it is a hypothesis that serious scientists take seriously, and it points toward the real worst-case scenario for the interstellar medium. Not a sudden catastrophe, but a slow, grinding influence over millions of years that has the potential to reshape habitability on Earth. What prevents us from predicting this more precisely? We don't know exactly what regions of the ISM our solar system has passed through in its 4.5 billion year history. We don't have direct measurements of past ISM density. We can only reconstruct the picture from indirect clues: isotope ratios in lunar soil, cosmic ray tracks in ancient meteorites, the geological record of Earth's ice ages. The universe keeps its own records. We are only just learning to read them. I want to be very clear with you as we enter this chapter. What follows is speculation. Informed, scientifically grounded speculation, in some cases supported by researchers at major institutions, but speculation nonetheless. I will tell you what the evidence says, and I will tell you where the evidence ends and the imagination begins. With that disclaimer firmly in place, let's talk about dark matter. Approximately 27% of the universe's total mass energy content is dark matter. A substance or collection of substances that has mass, exerts gravitational influence, and yet does not interact with light. We have never directly detected dark matter. We know it exists because of its gravitational effects on galaxies and galaxy clusters, because without it, the math of galaxy rotation and large-scale structure doesn't work. And dark matter is distributed throughout the galaxy, including in the space between the stars. The Milky Way's disk, where we live, has a dark matter density of roughly 0.3 to 0.4 GeV per cubic centimeter, according to current estimates. This is an incredibly thin density, like everything in the ISM. But unlike the ordinary matter of the ISM, dark matter passes through everything. It passes through stars. It passes through planets. It passes through you right now, at a rate of perhaps 1 million particles per second, depending on which dark matter candidate is correct. So in a very literal sense, you are already deep inside the interstellar medium of dark matter. It is everywhere, we just can't see it. Now, most physicists are confident that even if dark matter particles are constantly streaming through us, they do not interact with ordinary matter in any biologically meaningful way. The candidates best supported by current evidence, things like WIMPs, weakly interacting massive particles, or axions, would pass through Earth without leaving a trace. But let's enter speculative territory clearly marked as such. What if some fraction of dark matter is not uniformly distributed? What if it clumps, very slightly, in ways that create local overdensities? Some theoretical papers, published in peer-reviewed journals, not fringe publications, have explored the possibility that dark matter could concentrate in thin disk-like structures within the galactic plane, and that the solar system passes through this plane roughly every 30 million years. Lisa Randall, a Harvard theoretical physicist and one of the most cited scientists in her field, has proposed a version of this idea that a thin disk of a specific type of dark matter could trigger periodic gravitational disturbances in the Oort cloud, dislodging comets and sending them into the inner solar system. She has explored whether this mechanism might correlate with periodic mass extinctions in Earth's fossil record. This is not fringe science. It is a hypothesis by a respected scientist, published in academic contexts, with genuine debate around it. Most researchers are skeptical. The evidence for periodicity in mass extinctions is contested. The dark matter disk hypothesis has not been confirmed. But it is a remarkable thing to consider that the interstellar medium, expanded to include the invisible dark matter component that fills it, might be connected to the fate of species on Earth. That the great extinctions, the end of the dinosaurs, the Permian mass extinction that wiped out 96% of marine species, might carry, buried somewhere in their complex causality, a signal from the space between the stars. This bears repeating because it is extraordinary. We do not know what dark matter is. We do not know how it's distributed at fine scales. We do not know if it has any influence, even indirect, on life on Earth. The standard scientific view is that it does not. But the honest scientific view is that we don't yet know enough to be certain. And while we're in speculative territory, let's go one step further. Some researchers have proposed that the interstellar medium might carry complex organic molecules, prebiotic chemistry, or even microbial life, distributed across the galaxy. This is the core idea of panspermia, the hypothesis that life, or life's precursors, may be spread through space. The weak form of panspermia, that organic chemistry is widespread in the ISM and can be delivered to planets via meteorites and comets, is not controversial. It is well supported. Amino acids, nucleobases, sugars, these have been found in meteorites. Complex organic molecules have been detected in interstellar space via radio astronomy. The chemistry of life is not unique to Earth. The strong form of panspermia, that actual living organisms can survive interstellar transit and seed new worlds, is far more contested. The challenges are immense: radiation, temperature extremes, the timescales involved. Most biologists are skeptical, but a small number of researchers continue to take it seriously, and the discovery of extremophiles on Earth, organisms that survive in conditions once thought incompatible with life, has kept the hypothesis alive. What would it mean if it were true? What would it mean if the interstellar medium were in some sense alive, seeded with the precursors or even the survivors of biological processes from other worlds, drifting through the space between the stars for millions of years, waiting for a planet with the right conditions to land on? We don't know. We genuinely, honestly, humbly don't know. Let's venture, clearly and consciously, into the territory of informed imagination. I want to paint a picture, not of what is or what the science tells us will be, but of what could be if the more unsettling edges of current scientific speculation turned out to be correct. Think of this as the scientific equivalent of a fire drill, not a prediction that the building will burn, but an exploration of what we'd do if it did. The scenario begins not with a catastrophe, but with a change so gradual it's barely noticeable. It begins with a cloud. Our solar system, traveling at 70,000 miles per hour through the galaxy, has been passing through the local interstellar cloud for roughly 45,000 to 150,000 years, depending on the estimates you use. This cloud is warm, thin, and relatively benign. But the local interstellar cloud has an edge, and beyond that edge lies something called the local bubble, a vast, hot, low-density region of the ISM, carved out by ancient supernovae millions of years ago. And beyond that are regions of the ISM that are denser, colder, and far more complex. Now imagine that in 10,000 years, a blink of an eye on cosmic timescales, our solar system begins to enter a denser region of the ISM. The interstellar pressure increases, the heliosphere begins to compress. In our speculative scenario, this compression is significant, not catastrophic but measurable. the heliopause retreats from roughly 120 astronomical units to perhaps 80 or 90. This is still well beyond the orbit of Neptune, and Earth remains deep inside the heliosphere. But the heliosphere's reduced volume means it is less effective at deflecting galactic cosmic rays. Over decades, the cosmic ray flux reaching Earth's atmosphere increases by perhaps 10 to 20%. This would not be life-ending, but cosmic rays play a role in cloud formation. They ionize the atmosphere, providing nuclei around which water droplets can condense. An increase in cosmic ray flux might, in this speculative scenario, contribute to increased cloud cover, which reflects more sunlight, which cools the planet. Slowly, over centuries and millennia. Now add a second factor. As the heliosphere compresses, more interstellar dust particles begin to drift into the inner solar system. These are nanometer-scale grains, individually invisible, collectively capable of having optical effects over long timescales. The inner solar system becomes very slightly dustier. A fraction more of the sun's light is scattered before reaching Earth. Still not catastrophic, but cooling. Meanwhile, the increased density of the ISM around the heliopause creates a more turbulent boundary. The ibex ribbon intensifies, though no one on Earth can directly observe this. The Voyager probes, long since silent and adrift in interstellar space, are lost in the growing turbulence. Future probes at the boundary send back data that confuses researchers. In our speculative scenario, this is the point at which things become geologically significant. The cooling trend, driven by the combination of increased cosmic ray cloud seeding and reduced solar input, begins to shift Earth's climate in ways that take centuries to become obvious but millennia to fully manifest. This is not a Hollywood extinction event. There are no fireballs, there are no monsters. There is only the slow, patient pressure of the universe reminding us that we are inside it, that the space between the stars is not a backdrop, but a medium we are moving through, and that moving through different parts of it has different consequences. Over thousands of years, in our speculative scenario, sea levels shift as polar ice expands slightly. Agricultural zones migrate toward the equator. Species in high-latitude ecosystems begin to feel pressure. Civilizations that have built their agriculture around the current climate face the kind of gradual disruption that doesn't make headlines but reshapes history. Is this what happened before? Were the ice ages of the Pleistocene, at least in part, the consequence of our solar system moving through a denser region of the ISM? Were the periodic mass extinctions in Earth's geological record, the ones that occur roughly every 26 to 30 million years, according to some analyses of the fossil record, connected to the solar system's oscillation through the galactic plane, where dark matter and ISM density are higher? We don't know. This bears repeating, we don't know. The science is suggestive but not conclusive. The correlations are intriguing but unproven. But here is the most extraordinary thing about this speculative scenario. It requires no new physics, no exotic forces, no impossible technologies. It requires only that the universe continue to operate exactly as it does, that our solar system continue to move, as it has always moved, through regions of the ISM that vary in density and composition, and that those variations, over the long, slow time frames of geology and evolution, leave marks on the history of life on Earth. The space between the stars does not need to be hostile to be influential. It only needs to be variable. And it is very, very variable. Let me step back from our solar system for a moment and look at the big picture. Because the question of what the interstellar medium does to life isn't just a question about Earth. It's a question about every world around every star in the Milky Way. And that makes it a question about one of the deepest mysteries in science. Where is everybody? The Fermi paradox, named for physicist Enrico Fermi, who reportedly asked the question, "Where is everybody?" during a lunch conversation at Los Alamos in 1950, is the apparent contradiction between the high probability of extraterrestrial civilizations existing somewhere in the galaxy and the complete absence of any evidence for them. The Milky Way is 13.5 billion years old. It contains hundreds of billions of stars. Earth-like planets, we now know, are common. Life arose on Earth relatively quickly after the planet formed. By the numbers, the galaxy should be teeming with intelligent life. And yet, silence. One of the most compelling proposed explanations is the great filter. The idea that somewhere in the sequence from lifeless chemistry to spacefaring civilization, there is a catastrophically difficult step that almost no species ever passes. The great filter could be behind us. Perhaps the origin of life itself is extraordinarily rare, or it could be ahead of us, which would be a much more disturbing implication. Now, could the interstellar medium be part of the great filter? Let's think about this carefully. We know that the ISM varies dramatically across the galaxy. Regions near the galactic center are far more energetic, far more active with supernovae, far more intense in cosmic ray flux and radiation. For a long time, the galactic habitable zone was defined largely by these factors. The idea that life is more likely to exist in a comfortable middle zone of the galaxy, not too close to the violent center, not too far out in the sparse, metal-poor outer regions. But there's a more subtle version of this idea that involves the ISM specifically. Stars don't just sit in one place in the galaxy. They orbit, they drift. And over millions of years, they move in and out of regions of the ISM with very different properties, different cosmic ray fluxes, different densities, different passage through supernova remnants and molecular cloud complexes. What if the window during which a planet is in a stable enough environment, protected from ISM-driven climate changes, shielded from excessive cosmic ray flux, not recently bathed in a supernova's radiation, is actually quite narrow? What if most Earth-like planets around most stars experience ISM-driven disruptions on a frequent enough timescale that complex life never gets the chance to develop and persist? This is a hypothesis explored by researchers working in the field of astrobiology, and it connects to deeper questions about the nature of habitability. Planetary habitability is not just about surface temperature and liquid water. It's about long-term stability. It's about whether a planet can maintain livable conditions for the hundreds of millions of years required for complex life to evolve. And the ISM, with its variability, its supernova-driven shocks, its dense molecular clouds, may be one of the most significant drivers of long-term habitability instability in the galaxy. The Earth in this framing has been extraordinarily lucky, not just in having the right distance from the Sun, not just in having a magnetic field and a large moon stabilizing its axis, but in having spent the last several hundred million years in a relatively quiet, thin, benign region of the interstellar medium, inside a protective heliosphere powered by a stable, middle-aged star. If any one of those factors had been different, if our Sun were in a denser part of the galaxy, if it had passed through a molecular cloud during the Cambrian explosion, if a nearby supernova had blasted away our atmosphere 300 million years ago, we might not be here. The conversation about the Fermi paradox might be moot, because the species capable of having it would never have evolved. The space between the stars may not be empty. It may be one of the most significant filters in the history of life. There's a version of the interstellar medium question that almost no one talks about directly, and I want to bring it into the open, because it's both scientifically interesting and philosophically staggering. We have established that the ISM is filled with complex chemistry. We have established that prebiotic molecules, amino acids, nucleobases, sugars, form in the cold, dark hearts of molecular clouds. We have established that these molecules are delivered to planetary systems by meteorites and comets. We have established that life on Earth may have benefited from the chemical legacy of the interstellar medium that existed before our Sun was even born. Now here is the question. If all of this chemistry is distributed throughout the galaxy, carried by the ISM, seeded into every new planetary system, then should we expect life to arise wherever conditions allow? And if life arises wherever conditions allow, and if the ISM connects all of these worlds by carrying chemistry between them, then is the interstellar medium in some sense the medium through which life propagates across the galaxy? Not intentionally, not consciously, but structurally. The way a river doesn't intend to carry seeds downstream but does. This idea that the ISM acts as a kind of galactic biological transport network is taken seriously in the astrobiology community, at least in its weakest form, the transport of chemistry, not living organisms. And it raises a thought experiment that I find genuinely unsettling and wonderful at the same time. If life is widespread in the galaxy, and if the ISM carries the building blocks of life from world to world and system to system, then in some chemical sense, all life in the galaxy may share a common origin. Not a common ancestor in the biological sense, but a common library. The same set of molecular building blocks assembled into different structures on different worlds, following the same thermodynamic and chemical rules, expressing themselves in different forms. Life on Earth, life on some ocean world around Tau Ceti, life on a subsurface biosphere beneath the ice of a rogue planet drifting through the ISM itself. All of them assembled from the same chemistry, the same amino acids, the same nucleotides, chemistry that formed in the cold dark of molecular clouds that predated the Sun by billions of years. Are we alone? In the strict sense of extraterrestrial intelligence, we don't know. But in the chemical sense, in the sense of sharing the universe's molecular grammar, we may be profoundly, irreducibly connected to whatever life exists out there through the medium that connects all stellar systems. The space between the stars is not a barrier separating life from life. It may be the very thread that connects them. Let me come back from the philosophical frontier and ask a practical question. If we discovered, through Voyager data, or from a new generation of interstellar probes, or from an anomalous signal in our cosmic ray detectors, or from a sudden, unexpected shift in the ibex ribbon, that something significant was happening at the boundary of our heliosphere, how would humanity respond? This is not a frivolous question. It's a question about institutional capacity, about international cooperation, about the relationship between science and public communication, and about the gap between what scientists can know and what governments can act on. Let's start with detection. Our current capacity to monitor the interstellar boundary is limited. Voyager 1 and 2, both launched in 1977, are the only probes to have crossed the heliopause, and both of them are still functioning, sending back data, though with decreasing power and increasing signal delay as they move further away. IBEX, launched in 2008, continues to map energetic neutral atom flux from Earth orbit. The IMAP mission, the Interstellar Mapping and Acceleration Probe, is a newer mission designed to provide far more detailed measurements of the heliospheric boundary. But here's the limitation. None of these instruments were designed for real-time comprehensive monitoring of the heliopause. They are scientific instruments, not an early warning system. The data they return requires months or years of analysis. Changes in the ISM density or structure that might affect our heliosphere would unfold over decades or centuries, not days, but our ability to detect those changes early enough to be meaningful is currently very modest. If IMAP or a future probe detected, say, an anomalous increase in interstellar neutral atom flux, suggesting a denser cloud of ISM material approaching our heliopause, what would happen next? In an ideal world, a rapid escalation of monitoring assets, international scientific cooperation, immediate deep analysis by heliospheric physicists, and transparent public communication. The kind of response we'd hope for, the kind of response that our scientific institutions, at their best, are capable of. In the real world, the analysis would take time, the interpretation would be contested, the funding implications would trigger political considerations, and the question of how to communicate genuine scientific uncertainty to a public that expects definitive answers would create significant pressure. Because here's the honest truth about scientific communication of slow-moving, uncertain risks. We are not particularly good at it. We've seen this play out in climate science, where the certainty of long-term trends has been obscured by the complexity of short-term variability. Communicating the heliosphere may be beginning to compress over the next several thousand years with potential long-term effects on climate is not a message that any political system is designed to respond to. And yet, the information would be extraordinary. Imagine, for the first time in human history, we would have evidence that the interstellar medium around us was changing in a way that could, on geological timescales, influence the conditions on Earth. We would be looking at the universe and seeing it look back. The appropriate response, I think, is not panic. It is not dismissal. It is the same response that's always the right one when confronted with genuine scientific uncertainty about large-scale systems. Increase monitoring, invest in understanding, and be honest about what we know and don't know. There is also a philosophical dimension to consider. If we confirmed that the ISM was beginning to affect our heliosphere in a measurable way, it would be among the most profound scientific confirmations in history. It would confirm that we are not separate from the cosmos, not protected behind a perfect, impenetrable shield, but genuinely physically embedded in it, that the galaxy acts on us, not just as a backdrop, but as an environment with weather. Our cosmic weather forecast would finally have to account for conditions outside our solar system, and that would change everything about how we think of ourselves in relation to the universe. There's a tension in science, and in the way science communicates with the public, that I want to name directly in this chapter, because it applies exactly to the interstellar medium and everything we've discussed so far. On one side of this tension, the scientific instinct for precision and caution. Scientists are trained to not overclaim, to say our data suggests rather than we have proven, to acknowledge the limitations of their instruments, the uncertainties in their models, the alternative interpretations of their findings. This caution is not weakness, it is the engine of good science. It is what distinguishes science from ideology. On the other side, the public's need for clear, actionable understanding, and the reality that in a world of limited attention and competing priorities, nuance often loses to certainty. We might be approaching a denser region of the ISM that could potentially affect our heliosphere over thousands of years under certain conditions, is scientifically accurate. It is also, as a headline, almost impossible to communicate. This tension is not unique to the ISM. It applies to climate change. It applies to pandemic preparedness. It applies to asteroid risk. In all of these cases, the science is dealing with slow-moving, probabilistic risks that unfold over timescales longer than political cycles, and communicating them to a public and a political class that is optimized for immediate, certain threats. What do we do with this? I think the answer, for the interstellar medium specifically, begins with transparency. We should be honestly curious about the boundary of our heliosphere. We should be investing in missions like IMAP and whatever comes after it. We should be funding the astrochemists and the heliospheric physicists and the astrobiologists who are mapping this territory. And we should be, without panic, without exaggeration, but with genuine intellectual seriousness, taking seriously the idea that the space between stars is not an irrelevant void, that it has been shaping the history of life on Earth through the delivery of chemistry and the periodic disruption of our cosmic environment, since before the first single-celled organism divided in a primordial ocean. The balance between skepticism and openness is a difficult one to strike. Openness without evidence becomes pseudoscience. Skepticism without imagination becomes the kind of scientific conservatism that misses the ibex ribbon and is surprised by what Voyager finds at the boundary. The best science, the science that changes the world, lives right at the edge between what we know and what we're willing to imagine could be true. That's where the interstellar medium is right now, right at that edge. Let me take you somewhere for a moment. Not in a spacecraft, not in a simulation, just in your imagination with the help of some numbers that are, I promise you, exactly as extraordinary as they sound. The first radio signals that humans deliberately broadcast into space, the kind that carry the signal of civilization, strong enough to potentially be detected by another civilization's receivers, began propagating outward from Earth in the 1930s. The first powerful television broadcasts date from around the late 1930s and 1940s, which means that the outermost shell of humanity's electromagnetic presence in the cosmos is right now approximately 80 to 90 light-years across. 80 to 90 light-years, that sounds like a lot, until you place it in context. The Milky Way is 100,000 light-years across. Our little bubble of electromagnetic signal, the only evidence we have sent into the cosmos that something interesting lives here, is 0.09% of the galaxy's diameter, less than 1/10%. And within that bubble, our signals have been traveling through, you guessed it, the interstellar medium, through the local interstellar cloud, through the local bubble, through the thin, cold, vast, complex ocean of gas and dust and magnetic fields and cosmic rays that we've been discussing. Our signals have not yet reached the nearest star cluster of any significance, They have not reached the majority of stars within what astronomers call the solar neighborhood, the stars within 300 light-years of Earth. In terms of the galaxy as a whole, we have whispered into a room the size of a continent and covered approximately 3 feet. Now consider the light coming the other direction. The light from the nearest star, Proxima Centauri, takes 4.24 years to reach us. We see it as it was 424 years ago. The light from the center of the Milky Way takes about 26,000 years to reach us. We see the galactic center as it was during the last ice age of the Pleistocene, when Homo sapiens were still sharing the planet with Neanderthals. And the light from the most distant galaxies visible to our telescopes has been traveling for 13 billion years. We see them as they were when the universe was young, before our sun existed, before Earth existed, before the interstellar medium of the Milky Way had been enriched by the deaths of even the first generation of stars.